So yeah, I'm Eric Tamme. I'm with OnSIP, and today we're going to be talking about statistical analysis of traffic and VoIP networks for detecting abnormalities. So I know that Travis introduced me as talking about fraud, but one of the focuses of this talk is to look at traffic patterns, generally speaking. A lot of it is applicable towards fraud detection, but there's other things that we can look at too. So that's the gist of it. So before we get started, you might want to know who you're listening to. Like I said, my name's Eric Tamme. I'm principal engineer at OnSIP. I've been there for about 6-ish years. OnSIP is a hosted PBX provider. We're also a SIP platform for developers. And as I said earlier in one of our WebRTC roundtable talks as a question comment, is that we are the developers of SIP.js, which is a JavaScript SIP signaling library for developing WebRTC applications in the browser. I think that's it. So just an overview of what we're going to be talking about. First and foremost, why I use pattern recognition versus other things. We'll take a look at the test harness that I wrote for doing this presentation. And we're going to review 3 different methods of sort of looking at patterns in traffic. Specifically, a basic mean plus standard deviation, well, a number of standard deviations. Looking at something called the Hellinger's distance, the Hallin Obus distance, and finally, before we get started, I'd like to say that I'm not a statistician at all. This started out as just kind of a small project we were doing internally, and I found it interesting, so I dug a little bit deeper and did some more research, and I thought that I would present it here because maybe you'll find it interesting as well. So why pattern recognition? There's lots of different ways today to look at and detect fraud. You can look at a call prefix. You can look at the cost of a call. You can say, I'm going to set a billing threshold for a customer, and as soon as that's exceeded, this is going to be considered fraud. But the reason why we're using pattern recognition is because it's a general purpose tool for detecting different patterns and abnormalities in patterns within traffic. So we can use it to detect things like flooding attacks, DOS and SPIT attacks, actual fraud, and even misconfigurations. We had a customer who had configured calls to loop out the PSTN and back in through his switch, which started causing all sorts of problems. And our fraud, I say fraud, our pattern detection system signaled on that and said, hey, there's a problem here. So we contacted the customer and they said, thank you. So the test harness overview, if you want to, you can run this during the presentation if you want to just poke at it. It's on GitHub, github.com/etamme/VoIP statistics. I'll leave this slide up for a little bit. It's written in Python. It should work with Python 2.6, 2.7. I tested with 2.7. You need to install 3 libraries, matplotlib, numpy, and scipy for it to work. I tested it on Ubuntu 14.04. I then decided to update my laptop to the newest LTS and nearly broke it. But I got it working, and I also tested on 16.04. So it works with both those, but should also work on Windows, OS X, etc. Does anybody need more time for the GitHub link, or are you good to go? Oh, one more second. Okay. Okay. So an overview of what this test harness is and does. So it's a Python script, like I said, and what it does is it generates data based on a histogram that you supply it. So initially we were just generating random data sets saying, oh, I want to have calls that are between 20 cents and $2, but that doesn't give you any actual distribution that's, well, besides random distribution. And that doesn't really effectively reflect traffic patterns for customers. So the script at the top of it has a little data structure that allows you to supply the amount of traffic in a range of cost and percentage that you want, and it all has to add up to 100%. So for the purposes of this test, this is exactly what the traffic histogram looks like for the non-abnormal calling data, and that about 19% of the traffic is between 20 cents and 30 cents, 30% is between 30 cents and 70 cents, 21% looks like is between 50 and 70 cents, and 20 between 70 80 cents, and then it drops off significantly to be like 7% between 80 and 90 cents, and almost like maybe 2% for $1 to $2. So this is a moderately sort of accurate representation of a large percentage of our customer base being business users. their traffic often looks like this, and it's generally actually even a little bit lower. Their costs are usually under 70 cents for their average calls. Some of the tests that we're going to be looking at here can look at more than one dimension of data. And so the other data element that I'm using here is something that I'm calling the inter-arrival delta, which is effectively the number of calls per second. So it's the time between calls. For a normal customer, I've just set this to be between 1 and 1.5 seconds is normal inter-arrival delta. For our normal calling, we're generating 5,000 records, or 5,000 data points. And if there is any abnormal traffic that's part of the simulation, 500 records are generated for that. And it's actually interleaved into the normal calling data. So it's not just like calling data and then 100% fraud. It's intermixed with the existing normal data. And so for each of the sort of test scenarios that we're going to review, we will look at these 4 different sort of tests, as it were. The Hellinger's distance on the inter-arrival data, so the delta. Something called the Hallin-Obus distance on the delta and the price. Hellinger's distance on the prices of a call itself. And we'll also look at the mean plus 2 standard deviations on the price of the call. So those are the 4 different statistical method or applications we're going to look at. For the test harness script, I devised 6, I think that's 6, right? Different scenarios to see how different methods worked. And so the first ones we're going to be looking at is a DOS or flooding or a SPIT attack where there's no actual change in price. It's just somebody flooding the network with SIP traffic. And then we're going to look at high rate, that's so a low inter-arrival delta, and low cost fraud, followed by high rate, high cost fraud, and then low rate, so a normal 1 to 1.5 second arrival time or delta, high cost fraud, and then low rate, low cost fraud. And finally, if you're going to have a system that's detecting abnormal patterns in traffic, you have to make sure it doesn't trigger on normal calling. So we want to look at all these tests on normal traffic as well. So the most basic sort of pattern analysis tool we're going to be looking at, or statistical analysis tool we're looking at, is when the average of a set of calls goes over the mean plus the standard 2 times the standard deviation of what we're calling the training data. And so I'll back up a little bit here. This test harness, the way that it generally works is we have a set of 5,000 calls that we are generating, and that's going to be our training set. That's not any abnormal traffic. So we're going to calculate our averages, our standard deviations, and anything that we want to use as a baseline from that. And then what we're going to do is we take a moving window of 20 calls. So we're simulating traffic coming in real time. And then we take those calls and we apply these methods on those calls. So for this instance, we're going to take the mean of an average, or rather the mean of the 20 calls that's in the moving window. And if that average exceeds the mean plus 2 standard deviations, that's what we're considering our threshold. So that means that 95% of the traffic is going to be completely fine based on just the mean times 2 standard deviations, but 5% of the traffic is going to be considered outliers. And so there's different ways that you can avoid triggering on 5% of the traffic. And for this example, we're just keeping a rolling counter so that it has to trigger 10 times within 100 calls for it to actually be considered an alert. So that's the first method we're going to be looking at. The second method we're going to be looking at is something called Hellinger distance. And so as the slide here shows, I'm just going to read it. It's used to quantify the similarity between 2 probability distributions. It's closely related to Euclidean distance, and this is used on single-dimensional data sets, and they have to be probability distributions. So if you look in the slide here, you can see underneath the equation, it will compare the difference between the probability distribution on the left and the probability distribution on the right. And what it does is it return a value between 0 and 1, where 0 means they're equal and 1 means they're complete opposites. And so the formula is here for anybody who wants to look at it. It's on Wikipedia as well. Yeah, not a whole lot else to say about that. The next mechanism we're going to look at for analysis is something called the Hallin-Obus distance. And this, we're only going to be using it for looking at 2-dimensional data right now. But the Hallin-Obus distance can be used to analyze n-dimensional data so long as it's linear. And what the Hallin-Obus distance does is it takes information that, or rather data points that are similar and have a linear grouping to them. As you can see in this, the first picture on the left, that the data seems to fall along this blue line. And so the outliers that are at 2 on the blue line are not really such outliers compared to the outliers that are on 2 on the red line. So what Hallin-Obus distance tries to do is it will scale the data set based on the path where it lies. And then it allows you to, so it's removing the covariance from the data set to try and give you a better picture for calculating the distance from the center of the mean. So, and that's what it says here, is that multi-dimensional generalization for measuring how many standard deviations away some point is from the mean. So this is our first example. This is the DOS flood spit attack, and you can see on the left-hand side is the price of calling, and then on the right-hand side is the inter-arrival deltas. So everything's going really well for quite some time. We got an inter-arrival delta between 1 and 1.5 seconds, then all of a sudden, boom, it drops way down to 0.2 seconds. These are the different methods that we have done here. So in the top left corner is Hellinger's distance on the inter-arrival delta. And you can see clearly where that's alerted. I think that you guys can see there's a little red dot there on that green line. In all of these examples, a red dot is an indicator that the fraud or abnormality threshold has been triggered, and that's where it's been triggered in the calling sequence. So the top right image is, I believe it's the Hellinger distance on price. And since there was no actual change significantly in the price of the calls, it didn't trigger anything there. And likewise, the lower right image is the standard deviation plus, or sorry, 2 standard deviations plus the mean is the green line threshold, and that also did not trigger. The lower left is the Hallin-Obus distance, which is considering both the price of the call plus the inter-arrival delta. And you can see that that did trigger because it's considering both of those factors. Oh, and I actually wanted to say beforehand that these scenarios that we're going through, the intention is to make it so that we're going through the ones that are very easy to detect at the start to the ones that are the most difficult at the end. So this should be fairly simple for anybody sitting in the audience to say this looks like abnormal calling patterns. And that the price of our calls has gone from about 80 cents to $1 all the way up to $14. And our inter-arrival delta has dropped from 1.5 seconds, again, down to below 0.2 of a second. And so again, same layout here. So the top left corner, we can see is our Hellinger's distance on the inter-arrival delta, and that's triggered right away. On the top right, we've got our Hellinger's distance on the price. And that's also triggered right at the beginning of where this abnormal traffic has happened. The standard deviation plus the mean triggered on the bottom right-hand side very, very clearly. And then also the Hallin-Obus distance in the bottom left is triggered right at the beginning of that as well. So in this instance, high rate, low cost fraud, the traffic, the prices of the traffic are within the same range as the customer's normal calling patterns. So there's no actual significant derivation in the actual price from the sense that it's not outside of the distribution. All of the points fall within the distribution of their normal calling patterns, but they're going to be arriving at a higher rate because this is a high rate, low cost fraud example. And so we can see again, the inter-arrival deltas are much lower. So again, same stuff. Hellinger's distance on the top left of the inter-arrival delta is triggered. The Hellinger's distance on the price actually has also triggered because of the higher density of calling that the fraud is. Same with the standard deviation plus the mean, and also the Hallin-Obus distance on the bottom left. So in this case, again, should be pretty easy for anybody to see. Cost has gone through the roof, but the inter-arrival delta has stayed pretty much the same between 1 and 1.5 seconds, whereas cost, like I said, is up to $25. The Hellinger's distance on the inter-arrival delta has not triggered at all because that is all the same in this scenario. The distance on the price has triggered, as well as the standard deviation or plus the mean on the price, as well as the Hallin-Obus distance. So this is a trickier one. How many people in the audience think that they could see this and determine that this is fraudulent traffic? Anybody, show of hands? Maybe, a little bit. So again, we've got calling that's for the price that's exactly within the probability distribution for what our normal calling data is, and the inter-arrival delta is, again, pretty normal. There's only a little bit of interesting bit down at the bottom where the price for I say fraudulent traffic is fallen a little bit lower in this example. And so our Hellinger's distance on the inter-arrival delta has not triggered anything. The distance on the price has triggered, as well as the standard deviation on the price, but it's probably about halfway through where the abnormal traffic is. And the Hallin-Obus distance did not perform very well in this situation because all of this traffic looked the same as far as the covariance between price and inter-arrival delta. It has triggered, but nearly at the very end, so I would almost consider that not a very good indicator. And finally, the one that's the most difficult is actually no fraud and completely normal traffic. And so we don't want to see any indicators on this. And fortunately, for this example, we don't. All of the thresholds are within limits and nothing is showing up. So that's good. So what's easy to detect? We talked a little bit earlier, when you have something that's visually very impactful, it's much easier for the software to detect it. And that's the easiest when you have a difference in probability distributions in the sense that there are no matching buckets effectively. And so that the abnormal traffic or the fraud traffic doesn't even fit within the probability distribution of the normal traffic. It's very easy to detect when those things are out of skew so much. Difficult things to detect are when abnormal traffic falls within the buckets of the probability distribution of normal calling. And in this example, you can see this is actually, I believe, a Hellinger's distance on the price. And the distance only moves just slightly, but it's enough for this test to trigger on. So what I've learned as part of this process in putting together sort of a statistical analysis pattern system is that certainly one size does not fit all at all. And beyond that, tuning is a huge part of how this works and how things will be detected. So there's a lot of different ways that you can tune these systems. When you're looking at probability distributions for the Hellinger's distance and the Hallin-Obus distance, the types of buckets that you use can act as sieves and weights. So in the sense of if all of my customers do 80 to 90% of their traffic under $1, but they make 1 or 2 calls a month that are $5 or $10, you can create an exponentially larger set of buckets so that you start out with anything below $1 falls into this bucket. So 90% of your traffic falls into one bucket, and then you have a very wide bucket for calls that are anywhere between $1 and $10, and then you have one bucket for anything that's from $10 to $100, so that you catch much larger sets of data. So that's one way that you can tune things. Certainly, I think that the takeaway for me is that all of these different mechanisms perform within similar range of criteria, about the same. So I wouldn't say that one is better than the other or more accurate than the other for catching different patterns. but you can implement more than one to try and help increase the confidence in an actual threshold that you've triggered. And the Hallin-Obus distance is sort of an interesting thing in that because it relies on, I say relies, but it tries to take into account the covariance of data, you can start adding multiple different types of data points into that equation and discover interesting relationships to see what works and what is related as far as your traffic is concerned. In this example, I just used price and the inter-arrival delta, but you can take different types of data points and abstract that into the numerical. So if people are used to looking at prefixes to say this is an international call, you can do that using these mechanisms, and simply you have to put a probability distribution together that says how many calls have they made to this prefix in X amount of time, and you create a probability distribution over that. So this test harness is designed to allow you to kind of play with it a little bit, put different numbers in, and simulate different types of things. And so we are running this system now for our actual pattern detection and fraud detection at ONSIP, and we triggered one actually for the first time yesterday, so it was kind of fun to see that happen. Fortunately, they only got 10 calls through before it triggered, so that was good. I think that's pretty much it. Let me see what I have here. Yeah, no, that's it. So does anybody have questions?
Any questions for Eric?
Down here? Sure, I can repeat it.
When you were training your system, did you input the false data, or was that from your backlog of data? And you knew that it was actually an inconsistent call, and how did you determine that?
So the fraud that was detected recently, you're talking about? Or just our implementation, generally speaking?
I'm just saying, to train your data, you
Right.
run on back data. Was that something you, by hand, inserted data that was bad, or did you use, and how did you know that it was already fraudulent?
I'm still not certain I understand the question, but I'm going to
So
sort of
his
describe.
question was with regard to training data. What did you use for the training data
Right.
for fraudulent traffic? Did you use real fraud, or did you simulate fraudulent
Well, no,
traffic?
so the training data set is actually clean data. It's not fraudulent data. It's the opposite. And so the training data set is a clean data set. And so we took a look at 3 months worth of CDRs for every account across all of ONSIP. And we generated the standard deviation, the mean, et cetera, off of those data sets that were known to be non-fraudulent. And so we have that information for every single customer, and we've created a probability distribution for them. So each probability distribution is unique for each customer, so that each customer has different types of calling patterns, things like that. So that one customer who makes tons of international calls isn't triggering compared to another customer who only makes 5-minute or less domestic United States calls. And so the fraudulent data simply tripped the threshold, the required number of times, and it alerted us. And so, we have a couple of, we've gone through a couple of weeks of having some false positives every day. It's like, I'm waiting for it to actually trigger, hoping that it actually worked when you want it to work, but it did, so I'm happy that happened actually yesterday before I gave this talk, so I can say that it actually works in production.
We have a question right here. Go ahead.
And
Question
so,
was how
yeah,
quickly that you can detect fraud.
So it depends. It depends on the type of fraud or abnormal calling. And I said in this example, we triggered, I believe they made 10 call attempts. I think 3 went through and got answered, and we triggered after those 3 calls. So, but it really depends. These people were making calls to Cuba for $25 a call, so that triggered very quickly. Does that answer your question? I mean,
yeah, like how long after the calls were placed did you actually get notified?
Immediately. Yeah. So to explain a little bit further about our system, so we use OpenSIPs, and OpenSIPs is publishing dialogue events to an AMQP bus, and those get summarized together at a single location. And we have proxy servers all over the country, and so we want to do this detection in a single place where we have all of the information for all of the calling patterns, because accounts could be calling through multiple proxy servers. And so this all happens real time. As soon as a call ends, a dialogue event is published to the MQP bus. That goes over, gets put into Cassandra, and then we summarize this stuff together and put it through this fraud detection process. So we got to send an email alert. I think it was about 10 minutes after the call. I don't know if you remember over there, James. No, but I think it was about 10 minutes after they made their first call.
All right, we had a question way down on stage right there. Go ahead and yell it out. That's you on stage right.
What features of the call you have recorded for detecting it as abnormal? Second, have you tried true positive, false positive of your experiment?
So the question is, what features of the call are we basically analyzing to determine whether or not we're considering it fraudulent? And have we, what was the second part of the question?
Second is, have you analyzed how many true positive and false positive you have detected?
Okay, I got you.
You used 500 calls in
Mhm. And so the second question was, have we analyzed how many false positives we get versus true positives? So we are currently only looking at price for this implementation. This is a brand new system that we just deployed probably about 2 weeks ago. So as far as analyzing the true positive versus false positives, we got our first true positive yesterday. So we don't have a great deal of data to really give a statistically relevant answer to that question.
Yeah, you had one question there. Go ahead.
The question is, how granular are our data points? So it's every call. Yeah, so every call, the window moves one call, and one call falls out the back. And so we're continuously analyzing a 20-call window every time a call comes in. So it's a moving window. And so the system keeps track of this average that's moving, and as long as it's not triggering a threshold, it feeds that back into what's the training data set's average. So it not learns, but it changes over time. It adapts over time. You had a question down here? Correct. And so we've talked about doing an automated system where we will disable it and things like that. Sorry, the question was, are we just sending an email at this point? And the answer is yes. We didn't want to start shutting customers off immediately since we hadn't had any production environment to test it with yet. I think there was one or two more questions.
Go ahead in the white shirt.
For the training data, if I were to take previous CDRs from our network and feed it in, I might be feeding in fraudulent attempts also.
Absolutely.
How do I create a training data set?
Well, you have to make sure that you have clean data when you're creating your training data set. There's not really a different way to do that. Sorry, the question was, how do I create a clean data set for my training data?
You know, one question here is, when you're doing it based on price, you have something a statistician would call a non-stationary distribution, because every month you get new rate tables, and so your price changes. How do you guys deal with that?
Well, and so that's actually exactly what sort of, well, I addressed when he asked his question, is that we have, we take the new call in and create a new average, as long as that average does not trigger the threshold, we average it back into the training set's average. So it's an adaptive system. Certainly if your rate changes by a drastic amount very quickly, that would cause problems, but yeah.
All right, wonderful. Big round of applause for Eric.
Thanks.